Hello everyone, and welcome to Data Engineering with Subhadip. Today we're diving into a critical topic for any data engineer, building efficient incremental data pipelines using Python. We'll learn how to master merge logic and use metadata to create robust and scalable solutions. In this tutorial, we will first understand the core concepts behind metadata-driven incremental loads. Then, we'll dive into the powerful merge statement in BigQuery. Next, we will see how to tie everything together with a Python script. And finally, we'll tackle the common real-world problem of late-arriving data. First, let's clarify the difference. A full load copies everything, every single time. It's simple but becomes incredibly slow and costly as your data grows. An incremental load, on the other hand, is much smarter. It only processes records that are new or have been updated, making it significantly faster and more cost-effective. So how do we know what data is new? We use a metadata table. Think of it as the brain of our operation. It's a simple table that keeps track of our pipelines. The most important column here is last process timestamp, often called a high watermark. This tells our script where to pick up from on its next run. Here's a high-level look at our architecture. Our Python script acts as the orchestrator. First, it reads the last process timestamp, or watermark, from our metadata table. It then extracts new data from the source and loads it into a temporary staging table in BigQuery. Finally, it runs a merge command to intelligently update our final target table. Let's look at the code. The first step is to fetch the last high watermark. We create a simple Python function that queries our metadata table for a specific pipeline name and returns the last process timestamp. If it's the very first time we're running this pipeline, it will return none, allowing us to perform an initial full load. Once we have the watermark, we use it to query our source system. We construct a SQL query with a where clause to select only the records that have been updated after our last successful run. For the first run, we use a default old date to fetch all records. The result is then typically loaded into a pandas data frame. Before we touch our final table, it's a best practice to load this new batch of data, or delta, into a staging table in BigQuery. This isolates the incoming data, making the next step cleaner and more transactional. We configure the load job to truncate or overwrite the staging table with new data on every run. Now for the magic. The merge statement is an incredibly powerful SQL command that lets you combine insert and update operations into a single atomic statement. It looks at each row in our staging table and compares it to the target table based on a unique key. If a match is found, it performs an update. If there's no match, it performs an insert. Here is what the merge statement looks like in BigQuery SQL. We are merging our target table, aliased as T, using our staging table, aliased as S. The ON clause specifies the join key, which is the record ID. The when matched clause defines the update logic, and the when not matched clause defines the insert logic. Executing this from Python is straightforward. We define our merge SQL as a multi-line string, and then use the BigQuery client library's query method to run it. We wait for the job to complete, and can even get useful information back, like the total number of rows that were inserted or updated. Our system seems robust, but there's a common real-world problem: late arriving data. Imagine our pipeline runs at 9:05 and processes everything updated up to that point. But what if a record that was updated at 9:02 doesn't actually arrive in our source system until 9:06 due to network lag or system delays? Our last run would have missed it completely. The solution is to use a look-back window, or a grace period. Instead of querying for data strictly greater than our last watermark, we subtract a small amount of time, say 15 minutes, from that watermark. This creates an overlapping window, allowing us to reprocess a small, recent slice of data and catch any records that might have arrived late. In our Python code, this is a simple change. We import the time delta object, define our lookback period, and subtract it from the last watermark before building our extraction query. The merge logic we already have will handle any duplicates gracefully, simply updating them without creating new records. This makes the solution both effective and safe. Finally, and this is a crucial step, after the merge operation completes successfully, we must update our metadata table. We record the timestamp from the beginning of our current run as the new high watermark. This closes the loop and ensures the next pipeline run knows exactly where to start from. So to recap the entire workflow, we start by reading the last successful watermark. We use that watermark, adjusted by a lookback window, to extract new and changed data. This data is loaded into a staging table. We then execute a merge statement to upsert the data into our final destination. And finally, we update the watermark to prepare for the next run. By implementing this pattern, you gain tremendous benefits. Your pipelines become more efficient, saving compute time. You achieve significant cost savings, especially in consumption-based warehouses like BigQuery. Your data stays accurate thanks to the atomic nature of merge, and your system becomes more robust and resilient to real-world data delays. And that's a wrap on building incremental data pipelines with Python and BigQuery. I hope you found this tutorial helpful. If you did, please hit the like button, subscribe to the channel for more data engineering content, and share it with your colleagues. Thank you for watching.